All right. Ladies and gentlemen, good morning and good afternoon. I don't know exactly the time zone you are on. My name is Nikita Claudio, or Claudio Nikita if you wish. I'm from Winterthur Gas and Diesel. That's basically the company that is owning the technology for vertical two-stroke engines. And today I'm going to have, rather short introduction about Tier 3 technology. You may ask yourself why I have decided to go for this subject in particular. Many reasons. Primarily, I would say nowadays the fuel price is so low. The regulations, you have the IMO Tier 3 regulations. You have the IMO regulations with regard to sulfur emissions, with regard to CO2 emissions. And these are all stipulated, or most of them are stipulated in the Annex 6 of the air pollution, of MARPOL air pollution. Now, sulfur emissions, this is already enforced in the Baltic Sea. That is where the ships have to comply nowadays with low sulfurs. That means below 1%. Then you have the NOx emissions. This is a regulation that is supposed to come sometime 2016, but then there might be a delay for that. Nonetheless, if we look at the available technologies today, there are not many options. And if we talk about the two-stroke engines, which have to, most of the merchant ships, they have two-stroke engines, like large tankers, containers, bulkers, even ro-ro ships. They all feature a two-stroke engines. That is basically driving a propeller without a gearbox. So two-stroke engines, they are a large part of, let's say it's a large equipment that is part of the ship, of the merchant ships. Now, when you look at the available technologies, we have diesel, or basically, I mean, I'm not going to differentiate between MAN or Mitsubishi or Wärtsilä engines. I'm just going to talk about the technology itself. So if we look at that, then we have diesel engines. I mean, that is engines that are burning liquid fuels, and by that I mean heavy fuel oil. I'm going to use a lot of abbreviations just to make a side note. So heavy fuel oil, it's basically HFO. Marine gas oil is going to be MGO, marine diesel oil is going to be MDO, LNG, liquefied natural gas, and a lot of abbreviations which I'm going to detail, step by step. So every liquid fueled engine, that is HFO, MDO, or MGO, it's by default a Tier 2, so it's a Tier 2 compliant engine. What I mean by that is that there is no technology available today. There is no engine, in practical terms, that can comply with Tier 3 requirements of IMO. That is for engines running on liquid mode. If you look at dual fuel engines, which you might have heard probably, these are engines that can burn, it's dual fuel, it's, let's call it just a name for now, because these engines can burn any form of liquid. So they can burn HFO, MDO, MGO, and on top of that, they also have the possibility to run on natural gas. Now you have two types of technologies there as well. You have diesel engines, or let's say dual-fueled diesel engines, and dual-fueled auto engines. Let me call it like this. The diesel engines are what you may have heard as high-pressure engines, high-pressure dual-fuel engines, and the auto engines are what you may have heard as dual-fuel low-pressure engines. Now, there is, when you look at these aspects, at dual-fuel engines, there is only one engine today that can meet Tier 3 requirements, and that is the low-pressure dual-fuel engine, only in gas mode. Now, the fuel price, it's where it is today. The market is where it is. That means it's very low. That means basically that the demand for LNG has dropped a little bit. Has not disappeared, but just simply has dropped. I mean, in simple terms, the owners today don't have the incentive they had, I don't know, 1-2 years ago to go for LNG. And the reason you would go for LNG is to reach tier 3 compliancy if you go for low fuel, low pressure dual fuel engines, or simply because it's much easier to comply with EEDI requirements, which relates to CO2. Now, I mentioned at the beginning about sulfur emissions, NOx emissions, and CO2 emissions. The sulfur emissions and the NOx emissions are regulated by IMO. Also, the CO2 is regulated by IMO. The way IMO regulates CO2 emissions, it's by the implementation of EEDI, which is Energy Efficiency Design Index, EEOI, Energy Efficiency Operational Index. I'm trying to get the thing straight. And SEEMP. If I get that right, well, probably I cannot. So SEEMP, you may search for that, but that is basically a management plan for the shore-based personnel to track, or let's say to track and monitor the performance of the ships. So basically to follow up the implementation of the requirements. Because simply by having the ship compliant from the design stage, it's not enough. You have to validate that through model test and through full-scale, let's say, close watch on what's happening on the ship, you know, in terms of fuel burn speeds and everything that it's required for this to be compliant. Now, SOx, NOx, and CO2, all abbreviations. I'm going to skip the sulfur emissions in this presentation, at least partly. I mean, of course, I will probably touch a little bit here and there, incidentally, depending on which context I will get to with the NOx emissions. CO2, not so much, yes. Now, why I'm going to focus on CO2? The main reason is because me coming from Wärtsilä two-stroke division, nowadays Winterthur Gas and Diesel, if we look at the products we have, that is two-stroke engines, our main interest, our main focus, let's say, when it comes to the offering we have, is to provide a product that is compliant with the emission regulation. And sulfur, it's mitigated by having the right fuel type, either low sulfur, either burning gas, which virtually has no sulfur. CO2, it's a matter of how high speed your ship has. So if you have a ship with 40 knots, then you may have a very high CO2 consumption, which is closely related to the fuel you are burning. Of course, if you burn LNG or natural gas, the carbon content factor that is in the formula of EEDI is much lower, so therefore you will emit less CO2. But in the end, the amount of CO2 you are going to emit is proportional with the fuel you are going to burn. Now, the only aspect that is technology related, it's the NOx emissions, nitrogen oxides emissions. And this relates to the combustion process. Now, during the diesel cycle, you have higher formation of, you have higher temperature formations inside, and the higher temperature favor the NOx formation. So because of that, a diesel engine, I mean, in very simple terms, because of that, a diesel engine cannot reach tier 3 requirements. An auto engine, or let's say an engine that is running according to the Otto cycle, during the combustion process is developing lower temperatures. So if during the Otto cycle, there are not, let's say, these peak temperatures. And as I mentioned before, these peak temperatures favor the formation of NOx. So in case of Otto, this NOx formation, it's less, let's say. And because it's less, I'm not saying that it's not at all, it's just that it's less. And because it's less, you are compliant with, you are getting, let's say, to the compliancy level required by the IMO. Now, I dwelled quite a lot on the first slide. Let me jump to the next one, because I still have a number of them to go. Yes, okay, the market, right? I mentioned about that it's regulated by IMO. There are global caps implemented. There have been thresholds. Okay, initially it has started with tier 1, now tier 2, now tier 3. 2020, it's supposed that 2016, it's supposed that tier 3 is implemented at a global scale, but on the other hand, this might be postponed. So, I mean, tier 1, tier 2, or tier 3, it's based on a formula, And tier 3, it's a much lower requirement, or a much more stringent requirement on the engine manufacturers. And you can see there is a drop from 14.3 to 3.4. So that's quite a drop. If you look at SOx emissions or sulfur oxides emissions, in European ports, this is already implemented since roughly 2010. There is already point requirement worldwide. Then if we look at, no, sorry, that is coming 2020, it's 1% already in ECAs, in sulfur ECAs. Worldwide is 3.5, in 2020 that will become 0.5. When you look at the world map, you see here different colors. Now the yellow color means basically that's Baltic and North Sea. That's a sulfur emission control area, what people like to call SECA. Then we look at the North American continent, North America, and then we have East and West Coast, and this is a bit, yeah, green color. Now, what does that mean is that the US Coast Guard has implemented this emission control area completely for sulfur and for NOx. So that means any ship that is calling a US port on the East or West Coast has to comply with tier 3 requirements. Now, this affects ships coming into service, not the existing ones. This has entered into force sometime 2013, I mean the United States. When you look at the options that you have available for complying with these requirements, there are not many. I mean, for NOx purposes, you either use an SCR or EGR, or you burn gas. Yeah, this is basically the slide. So if you look at compliant, I mean, at ships to be compliant with both sulfur and NOx, let's say oxides emissions. Let's say first option, if you do no change, then that's not necessarily an option because you will be quickly out of business. The regulations will not allow you to operate anymore, so you will be out. Simple as that. You go to fuel switch, and that is, I mean, fuel switch means that from your traditional heavy fuel oil, which is a residual fuel, which is a dirty fuel, which has typically high sulfur content or had, well, it all depends on the price, of course. You want to pay for the fuel. So typically fuels had high sulfur content. Now, fuel switch means that you switch to a fuel with less sulfur content. This means you will be compliant with sulfur emissions. That is, by definition, low sulfur fuels, low sulfur content, therefore compliant with sulfur emissions. But then you need to be compliant with NOx emissions. I'm talking about either the future for, let's say, North Sea, Baltic Sea, when NOx is supposed to come into force sometime 2016, or if we look at the east and west coast of US, where you already have to be compliant. Now, low pressure SCR or SCR and EGR, let me use only these two. That is selective catalytic reducer, that is SCR, and EGR is exhaust gas recirculation. These are two technologies that you can employ to clean your exhaust gases of NOx emissions, or let's say of NOx. Yeah, okay, right. So you use these two devices. Now you will see that, okay, you have different suppliers, you have right, low pressure, high pressure, depending on where this SCR is located, and then you also have EGR, high pressure and low pressure. But predominantly you will see the ones that prevail actually for various reasons. I'm getting into that in a few slides. Then, so that was fuel switch. So that's quite easy, let's say, in a way, because you don't have to do any changes with, I mean, to your existing engine. You just need to add the SCR to be compliant with NOx, and then burn low sulfur fuels, and then you're compliant with sulfur emissions. Then we talk about add-on technologies. By add-on technologies, we talk about exhaust cleaning, or let's say exhaust gas cleaning for sulfur as well. And for that, you need a scrubber. So the scrubber does let's say in simple terms, the same as the SCR or EGR. It's cleaning your exhaust gases for sulfur. That means that you can continue burning HFO or residual fuels or high sulfur content fuels, which are cheaper. And yeah, you can still be compliant because you will have, let's say, imagine like a catalysator you have on your car, like Euro 4 or Euro 5 or Euro 6. It's pretty much the same, only that the scale is a bit larger than this. It's much larger. Then the other more neat approach, which every supplier, I mean not every, but only the two available that you have, and that's Wärtsilä and NDT, primarily for two-stroke of course, is to change to LNG. Now what LNG provides you, I mentioned earlier that for EEDI calculations, methane, or let's say the natural gas has lower carbon factor in the formula. So that is by definition the fuel is more favorable. It's more clean. Particulate matter, which I haven't talked about yet, that when you burn HFO, that is a very high emission of that. When you burn gas, it's a much cleaner exhaust. And well, gas typically virtually has no NOx, no NOx in it. Sorry, no sulfur. And yeah, then because you will, if you use low pressure dual fuel engines, then you don't need to have an SCR and you will be compliant with tier 3. I'm not going to talk about the other one yet, the other option. I'm getting to that in a minute. Now, if we look at the markets and where we are today, 2015 roughly, and then you see the share of tier 3 and tier 2 solutions and dual fuel solutions. Yeah, I mean, going for LNG on a ship, it's quite expensive. Going with SCR, it's also expensive, but not as expensive. Same with EGR. Doing nothing might not be an option actually. So this is basically showing the trend according to various sources. You see here. According to various sources, how the shipping will develop in terms of compliance with tier 3 over time. And you see that, okay, at least estimatively, from the estimation point of view, the tier 3 solution like SCR, EGR is gaining more ground than the TF. And primarily that is because of price of the technology itself. Now, let's talk a little bit about technical solutions. And you know, I talked a lot about high pressure SCR, low pressure SCR, SCR and EGR, and this is basically what they are, let's say in a nutshell, how they look like or how you would have them installed on your ship. And each technology has pros and cons, of course. I'm going to clarify what is high pressure SCR and what is low pressure SCR, but eventually they are all, say, the catalysator you have in your car for NOxes. EGR, it's pretty much the same. It's an exhaust gas recirculation, as the name implies. You get the exhaust gas, you get it washed, and then you get it dried, and then you get it back into your cylinder. So this process requires some equipment, requires some fresh water for cleaning, requires some blowers to dry the gas because you don't want to have water, too much water at least, not in your cylinder. So you know. Then the SCR, it's a bit different from the EGR. To that in a minute here. Okay, I'm getting back to this. Now the principle of SCR or otherwise of selective catalytic reducer. It's based on urea injection. You have a mixing pipe. Then during this, because you have high pressure and high temperature in that mixing pipe coming from the exhaust gas, then you have this split into ammonia. And basically what you need is ammonia to get into your catalyst, which is basically the brick in simple terms. Then you have a chemical reaction, exotherm reaction, so that is with exhaust of heat as well. And during this process, you get nitrogen and water. So, I mean, apparently it's a very simple system, and practically it's also a rather simple system. It's more difficult to manage all bits and pieces to come together, like the right size of mixing pipe and the right number of catalysts and the right size, diameter and length of this unit, because typically the SCR is a very large piece of equipment. It's not as heavy, but it's very large. You could compare it to about 1/3, very roughly 1/3 of the engine size. I'm not talking about the SCR itself, but the system, the entire system, because you have the mixing pipe. I get that one, yes, you see here. So I get the mixing pipe, I get the elbows because you have very large diameters, you have the air receiver, you have all the system here. Very large piece of equipment. Either it is low pressure or high pressure, they SCRs, they both work on the same principle. The only difference is the location of the SCR itself. Now, just a minute. Yes, here we are. Back to the main slide, let's say. Now, the high pressure SCR or the SCR itself, it's a temperature dependent equipment. The high pressure SCR has to go immediately after the turbocharger. Before the turbocharger. And low pressure SCR is typically positioned after turbocharger. By that I mean that the high pressure SCR needs to be installed very close to the engine, and the low pressure SCR can be installed in the funnel. I'm going to draw some parallel here, but they are not as black and white as I'm going to mention them. So we can argue that the high pressure SCR is the solution that could be easier implemented on new buildings, because then you design the ship and then you have more freedom to position this equipment around the engine. And then the low pressure SCR, I mean, we can argue that this is more favorable for conversions, where typically you already have an engine room, you already have a vessel in service, so you don't want to, destroy what you have paid for, in principle, and then you would put it somewhere in the funnel. Not saying that that is not disturbing, let's say, the exhaust pipes and that you don't have to rearrange, but at least it's much lower cost involved here. EGR is a solution that is attached to the engine itself. And then apart from that, you have, all the piping and recirculating, it's very close to the engine, attached to the engine practically. Then you have the ancillary systems that have to stay in the vicinity of that engine as well. Going to, this is just the diagram, very schematic diagram on how the system looks like. You have valves, you have blowers, scavenger, coolers, turbocharger and compressor. Okay, let me go a little bit about on this high pressure SCR. I'm going to jump on this slide here. Now, SCR, it's a very large equipment. It's not cheap, let me use this word. It's quite expensive. And of course, if you are not running 100% in ECA, you don't necessarily want to run your SCR if you're not forced to. And I'm saying that because the more you run your SCR, the more you have to do maintenance on it, and the more it's going to cost you. Now, I mentioned before that it's similar like on cars, but imagine like a much larger scale. So you have a number of valves that will bypass the SCR, bypass the SCR. Like if you're not in ECA, then from the air receiver, the exhaust air will go directly into the turbocharger. You see the red arrows here, and the blue lines here, basically these are the bypasses. You have the gates that are closed. Now, when your ship will enter into ECA, you will need to run your SCR. You will bypass, you will close actually. You have the blue line here. I don't know exactly if you see my pointer, but I have the lower left picture. I'm talking about that. You have the dark blue arrows and the light blue. The light blue is a valve which is closed, so that means from the air receiver, the air doesn't go directly into the turbocharger, but goes into the mixing pipe and then goes into the SCR. At the end of the SCR, hopefully you get a NOx-free exhaust gas, and that goes into the turbocharger and continues the path into the funnel and out. Now, the system, you have the urea injection system. I mentioned that one is located basically here, immediately after the air receiver or connected there. You have the mixing pipe. This mixing pipe needs to have a certain length. Now, you can use the urea injection, you can use urea itself, or have ammonia. I'm thinking that when you insert ammonia directly, you don't need to have such a long mixing pipe anymore. So you already have the product you're, let's say, hoping for by injecting urea or temperature pressure, you get the reaction and therefore ammonia. How the system looks like in a nutshell again, I mean, just schematically, in a large piece of machinery, you have, okay, imagine that this is not in scale, clearly. You have a control unit, you have the soot blowing valves. Now, why you need to have the soot blowing valves? Of course, I mean, the SCR, it's an expensive piece of equipment. You have a lot of bricks inside. Let me use the generic word for that. And you want to have this clean every now and again. Otherwise, you'll have a drop in pressure and lose efficiency on the reaction itself, and therefore not having the system running 100%, and therefore not cleaning your gases as expected. Okay, you need to have a tank for urea. You need to have your pump for that, and then you need to have the compressed air to blow the bricks for cleaning it.
Son toneladas de decir capacidad, 85 toneladas. ¿Me puede decir un buen...
Sorry. All right. When you look at this, it's not rocket science, and the SCR technology, it's not new. It's at least 20 years old. This has been employed in large-scale power plants applications. Only that for marine applications, this is rather new. Let me use the brackets, very big brackets for this. It's new because in marine application, in marine environments, you need to comply with a bit different sets of requirements. You have IMO coming into picture, and you know that complicates a little bit the things. It's not making the things necessarily impossible. It's just making them, yeah, in simple words, more expensive. All right. Looking at what we, Wärtsilä, wind to gas and diesel, have done. In that respect, for high pressure SCR, we have a number of references running since 1999. Then, whether you are aware or not, interested, there is a test engine, 6 Artiflex 50, which is DF actually, or has been non-DF and then has been converted to DF. That also has an SCR. A number of other ships which are running on high pressure SCRs. High pressure SCRs, just, I mean, to make it simple, high pressure SCR means before turbocharged, that means close to the engine, or otherwise very close to the engine. Low pressure SCR means, imagine it somewhere in the funnel. So you get more room in your engine room. Right, low pressure SCR. I mentioned a little bit about this. In both cases, low pressure and high pressure SCR, there is no modification required on the engine side. I feel that I need to tell a few more words about winter gas and diesel, what we do, and we don't manufacture the engines. We actually design the engines, we own the IP, and then we sell these licenses to our licensees in China, Korea, Japan, even Europe, and Vietnam to build the engines. So we don't build the engines ourselves. We develop the concept, the design, the product itself, and then let's say sub-suppliers are manufacturing this on our behalf. Of course, together with them, we focus on getting the quality and getting the product compliant as required. Now, when it comes to SCR, this is NOx, let's say cleaning the NOxes from the exhaust. This is something that we have to do. This is something that we need to do because it's a requirement from IMO and it's dependent on the technology itself. As I said, the sulfur is dependent on the fuel, and CO2 it's rather dependent on the ship design, ship type, and the willingness of a particular ship owner to run at, I don't know, 40 knots or 18 knots, which makes a big difference. So SCR is more tied to the technology. Now, of course, together with our licensees and together with our partners, not only licensees, we are very active on developing this low pressure and high pressure SCR. By that, I mean that, okay, since we don't manufacture this equipment, the only thing we can do, and we are involved with, in a lot of projects with suppliers and sub-suppliers, is to define the interface, like the mass flow, the temperature, the pressure that comes out of the exhaust side of a certain engine that needs to go into the SCR, whether it is high pressure and low pressure. So this is basically, in very simple words, what we are doing. Let's look a little bit at the components you will have here. I mean, okay, if we start with the low pressure SCR, you have the diagram on the right, upper right hand. This is a system that it's, I mean, the design of this system, it's owned by Doosan. Doosan is a manufacturer in South Korea. Typically, you have the reactor, which is the catalyst itself, the big piece, the big blue piece on the funnel, on the exhaust pipe you see. You have the ammonia generator, you have a burner, a blower, main valves, and the ammonia injection grid. It works in a similar way like I showed before. I'm not going to explain this further. Difference between low pressure and high pressure with regard to equipment. And yeah, I mean, okay, the high pressure has the downside that needs to be near the engine because of the exhaust temperatures, and the low pressure, okay, you need some extra components because it's higher up the exhaust chain. Your target temperature is somewhat lower, but you need to have some extra equipment. And then if we compare the extra equipment or the equipment you need for one or the other systems, I mean, they're all listed here, but primarily you will have this blower and you will have some extra fuel oil supply for the burner. So basically you will have to tune your two-stroke engine to burn a bit more fuel to get you to the right temperature level that you need to have at the inlet of the low pressure SCR. This means basically that your high pressure SCR has a lesser impact on the specific fuel consumption of a two-stroke, while the low pressure SCR has somewhat a higher impact on the specific fuel consumption. By higher means that it starts, or let's say it starts somewhere from 80% MCR and below, in case of low pressure SCR, and in case of high pressure SCR, this is somewhat 40% and lower MCR. So you will see a cap in that region, or let's say 1 to 3 grams more consumption of high pressure SCR below 40%, and 1 to 4 grams, let's say 1 to 3 grams from 80% and below in case of low pressure SCR. Size-wise, this is for a typical, well, not typical, but this is for a 15 megawatt two-stroke diesel engine. The size of such a unit would be something like, well, 4.3 meters, diameter 2.6, and then if you look at the other reactor, that is a low pressure SCR, you have the dimensions listed on the right side. So the low pressure SCR is somewhat smaller than the high pressure SCR. In the end, they both do the same. I was mentioning about the temperature and the impact of specific fuel consumption, somewhere about below 40, well, 40, 50. Yeah, because the target temperature for high pressure SCR is about 310 degrees Celsius. And in that range, you will have a cap because you need to tune your engine to burn a bit more to get to the right temperature. So that means compared with an engine that doesn't have an SCR, and high pressure SCR, you will see an increase in specific fuel consumption with the engine with the high pressure SCR attached. This is basis low sulfur fuel with 0.1% and below. Now, if you look at the low pressure SCR, the temperature variation is a bit different, but the target temperature is also different. Nonetheless, if you look at about 80, 90 or so, you need to tune your engine to burn a bit more, again, to get to the right temperature at the inlet. Otherwise, you'll not get the desired effect. Catalyzer will not actually perform. Similar way here, okay, the tunings. Basically what I mentioned, that you have this penalty of 1 to 3. And here you can see how a specific fuel consumption curve for a diesel engine, like a tier 2 engine, let me use these words. So the green one on the left diagram, on the left chart, more and more exactly, the green line means it's a tier 2 engine, more specifically a 6X52, 8 megawatts, 8.1, roughly 9 megawatts. And then when you have the SCR attached, you see a slightly higher specific fuel consumption from about 40 and below. Then on the low pressure SCR, because of the temperature variation, we have seen it in the previous slide, the yellow line, the green line, sorry, it's the tier 2 solution, and there you see the engine performance in terms of consumption. Like a tier 3 engine with the red line, you see that it has a higher consumption. This is basically the effect of SCR. And well, because fuel, it's a very important cost item in the ship operation. Typically, a ship owner would not like to have an engine that consumes more. On the other hand, he might be constrained by aspects like space in the engine room, like new building, conversion. So the options, you have options at hand. They all cost money. There is nothing for free, at least not yet. So it is going to be a higher consumption.
El capitán y el marinero mujer.
Yeah, this is basically very similar to the one before, just that it's a different tuning for the engine and how that affects the consumption. The available tunings for the engines, you have standard tuning, delta bypass, and low load tuning, both for high pressure and low pressure. You see that you have the bypass, delta bypass, and low load, where you can actually have the tier 3 solution, high pressure or low pressure, installed. I think I'm going to talk about a little bit about this tuning, what they mean, a little bit. Yeah, okay, the SCR can be applicable also to multiple turbocharger solutions, so it's not only applicable to single turbocharger solution. All this requires very close communication between the engine designer, like wintered gas and diesel manufacturer, like our licensees, SCR component supplier, which can be the licensee itself, the same manufacturer for the engine, or can be a third-party sub-supplier or supplier for the SCR solution, and of course the shipyard, because they have to build, or that's why they have to install and commission in the end the whole system. Let me talk about EGR now. Right, just to make a parallel here, Wärtsilä, or Winterthur Gas and Diesel nowadays, we have been developing in the last year the SCR system, the SCR solution for tier 3, while our competitor, MDT, the main competitor, let me put it like this, has developed the exhaust gas recirculation. They both serve the same purpose, cleaning the exhaust gases of the NOx oxides. One works better than the other, or otherwise, depending on the application, one is more suitable than the other. And you have seen in case of high pressure and low pressure EGR, SCR, what that means. That one is before turbocharger, means it's more crowded in the engine room afterwards, and the other one is after the turbocharger. Now the EGR system has its advantages. We will see them in a second. One of the main advantages is that you don't need to have urea. You use just fresh water to clean the exhaust gases. But then you need to have, so it's some, when it's not some, but it's a water treatment that you give to the exhaust, and then you dry it, and then you bring it back to the cylinder. just to compare a little bit the SCR versus EGR installation, I was saying that the EGR, it's a solution that needs to be attached to the engine. Attached in a way that you have very short pipe connections, because you have to recirculate all this, and you don't want to have, basically you want to minimize the losses there in the system. So on the left hand side, low pressure and high pressure SCR, we put them in the same under the same title because it's the same principle. It differs the location. High pressure SCR on the right side. It requires a bit more equipment, but on the other hand, the high pressure SCR doesn't require urea, which might be an advantage. Now, it depends on the operation profile, depends on the preference of the ship owner, depends on many factors. This is how typically this looks like. For high pressure SCR, or even for, you have a slide between high pressure and low pressure. Now, comparing high pressure SCR, and reason for that is because we Winter gas and diesel favor more the high pressure SCR. The main reason behind is because the impact on specific fuel consumption is far less than the low pressure SCR. Of course, there are situations where we have to go to low pressure SCR, either because of design of the ship, either because of the technology itself. So you have on the left hand side high pressure SCR, the equipment you need and the requirements for urea supply at 8 bars, compressor at 7.8. Then you have ammonia on the right side, ammonia tank, freshwater, sludge, and some extra power to run those devices in both cases. Actually, a bit more on the EGR side. Both SCR and EGR are technologies that are developed by the engine manufacturers. Winter gas and diesel, like the company I'm coming from, we are also developing EGR. This is, I think it's something that will come in the next 1-2 years. The technology itself is developed because there seems to be a potential market for it, but nonetheless, so far, we believe that SCR is the easier way to go. Right, this is a comparison between it's in a nutshell, it's a summary of what has been said so far. You look at an MDO, like a tier 2 solution, an engine running on or burning MDO, marine diesel oil, or distillate fuels. And then you have a high pressure, that is the blue line. And then you see the red line, let's call it red line, which is most of it, it's overlapping with, so that is the high pressure SCR, tier 3 solution. Most of it is overlapping with the blue line. As said before, around 40% and below, that line basically goes a bit higher. So it's a bit higher consumption with high pressure SCR in the low range of the engine operation. With EGR, because you have extra components and because you need to have extra power, translates to extra grams per kilowatt hour that you need to burn. Now, the higher you run your engine, or the higher rating your engine is running at, the more you have to run your EGR. If you don't run your engine at all, then basically you virtually don't need to run your EGR. Simple as that. So the higher cap is towards the higher engine operating range. Up to 4 grams, it is said here, all internal testing. From the operational point of view, operational expenditure, we can see here an estimation of costs in percentage from the operational expenditure for high pressure EGR and high pressure SCR. So if we say 100% is the total operational expenditure for, let's say, the orange stripe, that orange stripe comprises of sludge, power, blower, so the power for water treatment system plus the blower, fuel penalty, as we have seen in the previous slide here. Then we have that's ammonium. Then if you look at the high pressure SCR, yes, you have the urea, yes, you have a fuel penalty, and we can see it again here. You see the difference between the blue line and the red line, so it's far less. And electrical consumption, of course, because we have some pumps to run the urea, and in the end, Well, at least it's not the end. I have a few slides more. Sorry for that. Let me go to the capital expenditure. So far, well, it's an estimation, of course. There are no firm figures, and every price varies from project to project because of various reasons. I don't know, let's name a few. You have owners' preferences, you have long partnership with certain owners, certain shipyards. So negotiations, the price differs. But typically the high pressure SCR, it's a lower investment than an EGR, a high pressure EGR. If we combine the two, you would see that the high pressure SCR is somewhat the preferred solution from the cost point of view. Well, cost including the consumption. And as said before, SCR is the first choice for IMO Tier 3 compliant diesel engines. It provides lowest investment costs. It's a proven solution, at least coming from 20 years experience in the power plants, and it is applicable to the entire engine portfolio. Right, that was pretty much what I had for today. Of course, if you have questions, you can post them or you can send them by email. You have my details here. And if we have time, after my colleague will have his presentation, I could talk about a little bit more about the gas engines and gas solutions. Not with the presentation as such, but more like in words. All right, thank you very much.
Yeah. Hello, good morning, or good afternoon, everybody. My name is Joshua Moyogana, and I have been working for Wärtsilä for a few years already. And Professor Almathan has asked me to come to talk to you a few minutes about topics related to TrainMoS courses. And as you can see behind me, you know it very well. It says something like clean power investment analysis. The speech from my colleague, which I enjoyed myself a lot, is very much also related to that. When you are an owner and you have to think and decide what kind of technology, not all technologies cost the same, not all the technologies have the same impact in cost and price and environment, so you have to be very much aware of what you are doing and think very carefully before taking your decisions. Now, my topic is not that much related to technical issues, but still is very much related to investment analysis and especially clean power. Now, all of us here, you in the audience, and my colleagues and myself here, we are living in Europe, and we think of Europe as mainland only, which is not the truth. I mean, there's a lot of parts in Europe that are not in mainland, but they're in islands. And islands are all over the world, as you can imagine. And we have a curious reality in our hands that in today's world, we all want to take care of the environment. That's what clean power means. And today, let's be honest, clean power means making use of the natural gas as a fuel. And hey, it's easy to talk about that. I mean, talking about making use of the LNG as a fuel in Europe, mainland, or in other mainlands. But how about those that are living on not mainland, I mean in islands, all over the world, but also in Europe? I'm sure that many of you have been visiting, especially during vacations, different islands in the Mediterranean, and probably you have also seen the big power plants in all these islands. They have a quite curious dilemma today in these places. All of us, starting from myself, want cheap energy, and at the same time, we also want clean energy. Today, in mainland again, we have all access already, thankfully, to the LNG in Europe. But it happens that when you come to the islands, then you don't have that much access to the LNG. So if you still want to have cheap and clean energy, the one or the other. I mean, we all want to spend as little money as possible in energy. So at the end of the day, in all these islands, we have to go for the dirty heavy fuel oil, which is what they are burning at all the power plants in the island. So we think that this clean power should be democratized so that everybody can have access to that clean power, being it cheap. I mean, So we think that that's an issue, that's a topic in the minds of many people. Remember, I'm not talking specifically, not specifically about Europe, but this is thought globally, yeah, because not all the globe is as much advanced technologically as it is Europe, but why not also Europe to have this kind of thing? So if we want to take the LNG to these places, we have two problems. We have the problem of the storage and the regasification, which means investments. Again, clean power investment analysis is the main topic of the training course. So what can we do? What is the driver? Of course, we always have the possibility of building. Traditionally, the first idea is, hey, let's build a onshore terminal, typically a huge tank where we can get the LNG from vessel. We build a pier and port installation, and that's it. That's already invented. That's not rocket science. But it's not that easy and it's not that cost effective everywhere. We can have islands and smaller communities where it does not make sense economically to make such a big investment, not only for the community itself, who will have to pay finally for the energy, but also for the owner of the installation. The return of investments doesn't make sense. So at the end, this is another typical installation. Okay, we can put a so-called FSRU, which comes to mean floating storage and regasification unit, which is the in the right big one. It's kind of a floating unit where the LNG carriers come and be moored sideways, transfer the LNG to the FSRU, and then the FSRU is delivering the gas already to the community, to the island, to whatever it is. So what are the drivers if we want to find another option that is not that expensive as these two ones? Of course, when analyzing the investment, the customers, Barcelona, the world, drivers are typically shown there. First, importantly, if we are talking about analyzing investment, the investment has to be financially feasible. Because we are talking about a small amount of LNG, which means we have to find a solution in a small scale. Important to have that in mind, because the investment has also to be small, or as small as possible, but still making use of the LNG. It has to be flexible. Okay, the demand can vary, not from today until tomorrow, overnight, that's clear, but in the coming years, if you have an island, and why not? It's developing the tourism for the island. Maybe in 10 years' time, the need of energy in that island can be double or triple as what it is today. So you have to have a flexible solution also for that, not compromising your assets today and your money today to something that you don't know if we will need or not in the future. And of course, you have to take into account the physical limitations of the place where you want to place your infrastructure. Yeah, and see, you can have shallow waters, why not? And if you want to supply the energy with big carriers, you have to dredge the seabed and so on. So that's always time, money, permits, etc. And analyzing these drivers, we call it customers, but it's the worlds and countries, these islands. We say, hey, what do we have? What can a supplier like we, Wärtsilä, can provide? What do we have in-house that help to make this analysis and the decision making a bit more easier? We have in our in-house, a lot of expertise in both energy solution, which is producing energy, and also in marine solution, which is floating vessels and propulsion. And both cases are related in this case to LNG. Yeah? And of course, we have then the expertise to respond to customer needs. In the picture, you can see we are mentioning countries not in Europe. Indonesia and Caribbean is not still in Europe. But why not having those needs also here? Why not developing this kind of infrastructure in islands that today are not that much interesting? Who knows? And of course, and finally, we jump into this because we do believe that the gas is the future, is the clean energy that we should all be making use of in the coming. So then, so we have the first two options, the typical two options, which is the land-based installation. Typically, we can see it almost everywhere, not everywhere, but in many places. The FSRUs, which is also being used all around the world. So, and then we come with something easy, cheap, put it in commons, and flexible, which is what we call the Wärtsilä Mobile LNG. It is basically a barge, LNG barge, that you transport as shallow installations, shallow waters. You can install it when it's needed, and it supplies directly the gas to either the community, being used wherever it's needed, or also to an energy power plant that can be just sideways there or whatever it is. So this way we can provide the community, whatever it is, can have access to cheap and clean energy. Let's see, back to the analysis. We have to take into account the different aspects when we are analyzing the way we want to supply energy to a place that doesn't want to be out of the clean energy sources. So first one, back, asset flexibility. And we are analyzing the three options. No? Onshore terminal. Flexibility, no way. It's fixed, it's built there, and it stays there until the end of the days. That's clear. It's not something that you are going to move from here to there anytime soon or in the future. No way. FSRU, of course, it's flexible. You can put it where it's needed. When it's a demand of gas, there are already a few of these installations around the world. They are big vessels, but of course, as far as they are vessels, they are flexible and they can move around. And of course, the mobile, our idea of a mobile LNG barge, that's clearly flexible. More things to take into account. Weather sensibility. Onshore. Suppose that onshore terminal is a fixed stuff, it's a building, so it should not be sensible to weather. Some of you can remind now of Fukushima and think that maybe it's not that clear, they are not sensible to weather, but okay, let's not talk about extreme conditions in general. But of course, the floating installations are clearly sensible to the weather. That's something that has to be taken into account. CapEx, investment itself, well, the money you're going to put on the table. In terminals, high. Okay, maybe not necessarily that high in Europe, but around the world, yes, because you don't have that much amount of prepared personnel, technical experts, professionals everywhere in the world. So probably in many places you have to hire them from Europe or from America, So you have to hire really costly personnel to make it happen. FSRU, yeah, it's costly, that's clear. It's not a little vessel. It should not be that costly. I mean, the shipyards around the globe can build it at a reasonable price. And the batch is not a small thing. You can build as many as you want, but a unit of it's not that expensive. Operate the installation. One is you have the terminal onshore, fixed and finalized and working. Operating the terminal is not that expensive. You don't need that many personnel. The floating installation, yes, sure, because you have not only the personnel taking care of the regas installation, but as far as it's a vessel, it can be ready for departing at any time. Emergencies for whatever. So you have to keep personnel on board. The engines, the propulsion has to be ready for starting up, have to be warmed up all the time. And you, of course, are consuming energy to keep that running. The Wärtsilä Mobile LNG, no, the operation is cheap again. Size, comes to size, terminal is size, it's okay, you can build as small as you want. FSRU, no, it doesn't make sense to make an FSRU vessel smaller than the minimum, which is today around 120,000 cubic meters of LNG. Below that doesn't make sense. It breaks the rules of the economy of scale. And LNG mobile, that's cheap, you can do it. Onshore permits. Yeah, you have to ask for a lot of permits today. When you have to make any building related to energy onshore, you know it already. And for the vessels, floating installation is not that important to have onshore permits. Apart of those of getting the permit for mooring and berthing in the place. And the delivery time. Building a small terminal should not take, the construction itself doesn't take that long, but from the moment you start asking for the permits, etc., it can take between 1 and up to even 4 years to get the installation up and running. FSRU can take between 2 and 3 years, depending on the shipyard, schedules of the shipyard, workload, etc. And the mobile installation can have it almost soon. So it's a matter of making the decision, and in a couple of years maximum, you have already the installation running. And so this is an image of what we think that could be matching future demand of LNG in places where the LNG today is not available, and they don't want to refuse to have cheap and clean energy involved. So this kind of installation, this is and I think we are the first providing this kind of solutions to the market, can handle small amounts of LNG efficiently, which is important. Efficient comes to match with investment costs, and small amounts, which can be in a small island what they need. Yeah? The infrastructure you need onshore is not that important at all. You can build it very easily, and you can transport it to places where you don't need even to have to do prior to having the installation, to make a lot of dredging, which is again costly. So this is flexible and expandable, which means you can make it as big or as large as you want. Okay. Not taking stupid decisions, but this picture, sorry for it, it's not that clear, it's a PDF. But you can find 2 lines of numbers in below half of the slide. The first one you should look at is the megawatt figures. These are typically what could be power plants that can be installed anywhere. You can have power plants going from 50 megawatts to up to 800, and of course bigger. And depending on the demand, of course, you can have a small one. And a small one typically is, we're talking about, of course, power plant running on LNG. They are typically refilled twice a month. So, and the needs of LNG for instance, a 50 megawatt power plant with an average efficiency of 46%, and this is the typical values of calorific value and density of the typical LNG. If you want to refill it twice a month, you need a tank of 7,500 cubic meters, and so on. So double for 100, etc. So for the smallest in this chart again, power plant, 50 megawatts, we can provide an LNG batch, the basic one, as we call it, which has almost nothing on board apart of the tanks and the regas unit, which is enough. From as low as 5,000 cubic meters up to more than 10 and up to even 15. And of course, if in the future you need of energy, you can add more batches up to, why not, to 30,000 cubic meters. Second option, if you want to have a more autonomous LNG batch, we can be provided what we call an all-inclusive LNG batch. It has also not only the gas unit on board, but also controls, and it's self-supporting when it comes to energy for the regas unit, and it comes from a smaller one, could be around 10,000 or 12,000 cubic meters up to more than 30. Of course, the whole range of power plants can be supplied with land-based LNG terminals, but in the previous slide we already saw the limitations, or the constraints, the pros and cons of the land-based terminal. And the FSRUs are useless, are too expensive and too costly, below 120 cubic meters. So this is it. So just to give you a hint of how it would look like, this would be the smallest LNG storage and regasification batch that can be provided to a community that is demanding it. The storage volume can go from as low as 5,000 cubic meters to 15. This is a bilobular C-type tank. Bilobular, you can also see one cylinder there, but they are, let's say, two attached to each other. It's bilobular. The width of the batch should be no more than 32 meters, which curiously matches the Panama Canal, the existing one. And the length should go, depending on the amount of cubic meters you want to store there, of course, from between 80 and 150 meters. The important point, draft, maximum should be 6 meters, which is almost nothing. You can find easily 6 meter draft waters almost everywhere. So that's an important point. And the weight, not important, but it should be, just to make an idea of what we're talking about, within 5,000 tons and 10,000 tons, the biggest one. There's a couple of more views of the same installation, and this could be the biggest one, where we have 2 bilobular tanks on board, and the regas unit would be 180 meters long and 32 meters wide. And this is what we call the all-inclusive, which will be in places where they want the batch to be self-supporting for everything. So it should have also its own control room and also the power source, 1 megawatt genset there, for being absolutely self-sufficient. And this one should go between 10,000 up to, why not, almost 40,000 cubic meters. And you can see the length is the same, and then the width is going up, and especially the draft is quite big. So that makes it go up to 37.5 thousand cubic meters. And the weight again can go up to 20,000. This is the solution. This is another use of the same solution. Again, what makes sense to all this is to have the possibility of having cheap and clean energy in places where today, and this is a fact, they have to go always to dirty heavy fuel oil. And of course, the solution can be even more complex or more complete, so to say, because that can be combined with also a floating power batch. In this picture, you can see the complete solution. In a community that needs clean power supply, the decision can be made today, and in less than 2 years, you have the installation up and running where it's needed with clean and cheap solution. This is not new in our installation, because in the past, the two on the top are actual pictures of power batches, as you call them, now it is in the, and both I think they are in the Dominican Republic. I've been visiting them both with heavy fuel oil, in this case engine. They are already at, not all but speeding as the power installation, and the below one is quite new. It's already being delivered, but this is a render of the design, where we again ensure the most important things. Yeah, the mobility, you can took them where it's needed, and when it's not there, you can take it another place where the need is more, or simply that the place where the batch is located, the community or the country wants to transform it into a different thing, and then they think that the best location for the new power plant is another place. You can take it and move it so that you can free the space for other issues. The construction time is really short. In less than 2 years, again, you can have it delivered. The design is already well proven, believe me. It's been there working for already quite some years. The fuel choice is also flexible. This showing the pictures are running on heavy fuel, but of course, if you have put engine that can run in either in fuel, heavy fuel, or in LNG, you have the full flexibility of gas. You can make it as big as you want. You can add more modules so that you can do the investment when it's really needed, so that you match the demand of the energy and the clean energy on site, because they are built to cope with the most strictest environmental standards, and the operation and maintenance also is something that's already well proven, and there's no secrets therefore. It's not costly. And yeah, below you can see the here called limited. It's going to be delivered for Papua. It's under construction with the brand new 32 engines now operating heavy oil. But why not? They could be operating in LNG in the future if they are transformed into DF engines. And the picture on top is the onshore terminal that we also are delivering. With this, what we say is that we are not promoting specifically the LNG batch. What we say is that the community have to have in hand all the solutions for all the types of needs. Obviously, it's the onshore terminal that we are delivering in Finland, in Tornio. And of course, again, we also are delivering regas installation for FSRUs and for important and different owners and shippers all around the world, heavy industries in Hyundai, South Korea, Petronas in Malaysia, and some other that's already running. So this is what we have. So again, as a summary, clean power investment analysis. Clean power, why should a small community not to be able to have clean power? Why do they have to have, as they have today, only heavy fuel oil power plants? They can have power plants running on LNG, but how can we deliver? How can the LNG be delivered fast and cheap without making huge investments? Because it's not only the community, but also the utility companies do not. They are still reluctant to make investments that in the future are not giving a return of investment that is reasonable. So with this kind of solution, the floating budgets, we can say to the world and the communities, to the islands specifically, that there is no way that they have to refuse to have clean power at a reasonable. So this is it from my side. I hope you have enjoyed it. I have no time for that. Thank you.
I think that you have a question.
Really?
Question after thanking you very much for your presentation. Is asking, I would like to know which could be the suitable voltage of generating set for power batch.
Well, okay, that depends on how complicated or how much money you want to invest. But these power batches that I show you, this couple of ones, the Estrella del Mar and Sultana del Este, they are directly supplying to the national grid in the Dominican Republic. So you can adapt them to the needs of the 6.0 million voltage. It can be even lower if the community is small and you don't have that important need. You can be as low as demand. You can make it as complex or as simple as you want. There's no limitations there.
And if possible, I would like to know which could be the price of the power batch.
That's a nice question that I'm afraid I cannot reply on that. Simply because I don't have myself the answer for that. What I can tell you is that today, actually, we are already in conversations and even in negotiations with at least 3 different customers all around the world for these solutions, but I myself, I cannot reply on that. But again, it's a much more cheaper than any complex or onshore installation, let alone any kind of huge FSIU that makes no sense in a small community.
More questions? No? So, can we call it a day?
Thank you.
Thank you as well.